Hi, this is chapter 16 from Master Math Mentors AP Calculus AB Manual. It is on related rates. In the opening section, we use the basic definition of calculus as the mathematics of change. We define words that were synonymous for change, whether they be positive or negative, such as increasing, decreasing, growing, shrinking, etc. Changes occur over time. So when we talk about how a quantity changes over time, that is a derivative with respect to time. And mathematically, when we talk about rates, rates are derivatives, and we call those related rates. This first section of chapter 16 is going to help us get the idea down of what a related rate is. So we're going to fill in this with variables and calculus notation. Looking at number 1, part A, write equations that describe these statements. Be sure to label your units. So in part A, John is 5 feet tall. So his height is equal to 5 feet. And at this current moment, he's growing at a rate of 3 inches per year. So that would be the derivative of his height with respect to time. How is his height changing? His height is changing at the rate of 3 inches per year. Part B, a storm is 750 miles from shore. So we can use, typically we don't use D for distance. Let's use S. So in this case, the distance that this storm is from shore is 750 miles. Now, how is that changing? So the derivative of the distance of the storm with respect to time is equal to 200 miles per day. However, since this distance is shrinking, it is getting closer to shore. So the 750 miles is actually getting smaller. This rate is actually a negative rate, negative 200 miles per day. The radius of a puddle of water is 4 feet. So R is equal to 4 feet. And it's not changing. It is staying the same. If it is staying the same, the rate is equal to 0. And we need not put units if the rate is equal to 0. Part D, we have a cone, and the volume of that cone is 12 pi feet cubed. So let's call that capital V is equal to 12 pi feet cubed. And that volume is shrinking. So the derivative of the volume with respect to time, that's basically the rate, like how is the volume changing? And it is shrinking. So that's going to be negative 5 pi inches cubed per minute would be our rate for that one. E, a car is 2 miles from a bridge and approaching the bridge at 20 miles per hour. You try that one. I'll give you a second, and then we will fill it in. Again, we normally don't let distance be D, but I guess you could. It's just confusing when you have like D, D. So normally we don't let distance. So let's let it be X in this case, I guess. The car is 2 miles from the bridge and approaching at 20 miles per hour. So the rate that X is changing with respect to time is 20 miles per hour. But since it is getting closer to the bridge, that 2 miles is getting smaller. So our rate would actually be negative. RF, the angle that a drawbridge makes with a road is currently 10 degrees and is increasing at 3 degrees per second. I'll give you a second to write that one down. Theta is equal to 10 degrees, and d theta dt, the rate that theta is changing with respect to time, is 3 degrees per second. And since that's increasing, that would be positive. Part G and part H are a little bit confusing, but as long as you can get the first part, I think you'll be okay. The second part talks about the second derivative. It does get a little confusing, but I think as long as we can understand the first part, we'll be okay. the value of a stock is 50. So let's let the value be equal to $50. And it talks about how that value is changing. It's saying that that value is increasing. And if that value is increasing, we know that that has to be a positive number because the value is increasing. But then it says it's increasing, but not as quickly as it was last week. This brings in the second derivative, which I'm not sure you'll understand at this moment, but that's okay. It's still increasing, but not as quickly. And since it's kind of slowing down, the rate that it's increasing is slowing down, the second derivative would be less than 0. All right, part H, the price of gas is $2.50. So we're just going to let the price of gas be equal to $2.50. And that price is going down. So how is the price changing? The price is decreasing. And since that price is decreasing, we know that that rate has to be negative. And it says it's decreasing, but not as fast as it was last month. So it's decreasing slowly. It was decreasing faster last month. So the second derivative in this case would be positive. And that part is a bit confusing, but not as fast as it was last month. So it's decreasing slowly. It was decreasing faster last month. So the second derivative in this case would be positive. And that part is a bit confusing. All right. Number 2, a rectangle whose sides are changing is 10 inches by 6 inches. 10 inches by 6 inches. We want to write formulas for both the perimeter and the area and how fast each is changing in terms of L and W, the length and the width. So the perimeter of a rectangle, the perimeter of a rectangle is equal to 2L plus 2W. And how is that changing? We're going to use implicit differentiation to take the derivative of every single variable with respect to t, with respect to time. So like when we did implicit differentiation earlier, we did dx, and we didn't have to write that part. But in this case, we're going to have to write it every time because we're taking the derivative with respect to time. So the derivative of p is just 1 dp dt. The derivative of 2L, is just 2, but that's dl dt. Plus the derivative of 2w is just 2, but we're taking that derivative with respect to time. All right, for the area, we know the area of a rectangle is equal to the length times the width. And to change the area, we're going to use an implicit differentiation to take that derivative, and we're going to have to use product rule this time. The derivative of A is just 1 dA dt equals the derivative of L is just 1 times W, 1 times W, but we took the derivative of L with respect to time, plus now we're going to take the derivative of W with respect to time. So it's going to be L times the derivative of W is just 1 dt dt. That's an L, not a 1. It looks like a 1, but it's definitely an L. All right, part A. They give us some information. They say its length and width are increasing at 2 inches per second. At 2 inches per second. So what do we know? In this case, we know that dl dt is equal to 2 inches per second. And we also know that dw dt is equal to 2 inches per second. So we can plug that into our formula up here, this one right here, to figure out how the perimeter is changing. So we're actually solving for, they want to know dp dt. So dp dt is equal to 2 times dl dt plus 2 times dw dt. But we know how the length and the width are changing in this problem, so we can plug that in. and they're increasing at a rate of 2 inches per second. And 4 plus 4 is 8. So the perimeter is changing at 8 inches per second. And if we're confused about the units, like how'd you know the units were 8 inches per second? Well, you have 2 times 2 inches per second, which is 4 inches per second, plus 2 times 2 inches per second. If we write out the units, they will always take care of themselves. 4 inches per second plus 4 inches per second is 8 inches per second. So if we look at the how the area is changing, we're going to use this formula. So we're actually solving for dA dt this time. So we get dA dt is equal to the width times dL dt plus the length times dW dt. And we know what the width and the length are. We know that they were given to us earlier. So we get dA dt is equal to the width. In this case, the width was 10 inches. That was our width, 10 inches. dL dt is 2, plus our length was 6 inches. And that was given to me up here. At this moment, I don't think it really matters which one we do first, which one we deem the width, and which one we deem the width, and which one we deem the length. 10 times 2 is 20, 6 times 2 is 12, 20 plus 12 is 32, and we're talking about area now, so that's going to be, our units are going to be inches squared per second. And if we were to work this out, you would get 10 inches times 2 inches per second. And if you multiply that together, inches times inches is inches squared per second. All right, part B, same idea. We're going to use the same formula, or the same formulas, rate of change formulas, related rates that we used for part A, but now our sides are actually shrinking. Our length and width are decreasing. So dW dt is equal to negative 2 inches per second, and dL dt is equal to the same thing. It is possible that it could be equal to two different things, changing two different ways. So our change of perimeter, we're going to use this formula again. I'm just going to go ahead and plug everything in that we know. dP dt is equal to 2 times. The length is changing at negative 2 plus 2 times the width is also changing at negative 2. And we get negative 8 inches per second. We're talking about perimeter. So the units for perimeter are just inches. And how's that changing? It's changing at negative 8 inches per second. All right, change of area. We're going to use the W dL dt plus L dW dt formula. So dA dt is equal to the width. We said it was 10. The length is changing at 2 inches per second. So we're looking at this formula right here. The length was 6. And the width is changing at 2 inches per second. So we end up with negative 32 inches squared. Area would be units squared per second. And that's how the area would be changing at that moment. All right, part C, we talk about the length is increasing and the width is decreasing. And this is where, at least for the area problem, this is where this would probably matter about which one's the width and which one's the length. And they don't really tell us which one's which in this case. So it's very likely that I did get them mixed up. So remember our change of perimeter formula, dW dt is equal to, scroll back up, 2 dL dt plus 2 dW dt. So we're going to plug that in. We get 2 times dL dt. So its length is increasing. So dL dt would be equal to positive 2 inches per second. And its width is decreasing. So dW dt would be equal to negative 2 inches per second. So we get 2 times dL dt is 2 plus 2 times dW t is -2, and that's equal to 0. So if the length is increasing at 2 inches per second, its width decreasing at 2 inches per second, there's no change actually in the perimeter. dA dt, remember dA dt was equal to the width times dl dt plus the length times dw dt. We know the width was 10. dl dt is changing at 2 inches per second, which would be 2, plus the length, which is 6, and the width is changing at -2. It's actually decreasing. So we end up with 20 plus 12, that's 12 inches squared per second. If we were to switch the width and the length, we would get -12 inches per second. If you go back and read the problem, it's not clear which one is the length and which one is the width. It says its sides are 10 inches by 6 inches. And I started with this being the width and this being the length. It's very likely that this could have been the length and this could have been the width. And then that would have changed our answer only on this very last problem. It would have been -12 instead of +12. Part D, its length is decreasing at 4 inches per second. Its width is increasing at 2 inches per second. Now that idea of the length and the width in this case is also going to affect my answer here, depending on which one we let be the length and which one we let be the width. We let the length be 6 earlier, and we let the width be 10. So we're just going to stick with that. It says the length is decreasing. So dl dt is equal to -4 inches per second. The width is increasing. So dw dt is equal to 2 inches per second, and that's a +2. So dp dt, using the same formula we used before, is going to be equal to 2 times, how is the length changing? The length is changing at -4 inches per second, plus 2 times dw dt is increasing at 2 inches per second. So the perimeter actually would not be affected by which one we let be the width or the length at the beginning. But the area might be off by a sign. So remember, dA dt was equal to W dl dt plus L dw dt. We said W was 10. We said the length this time is changing at 4 inches per second. So we get 10 times -4 plus 6 times the width is changing at 2 inches per second. That's -40 plus 12. -40 plus 12 is -28 inches squared per second. And again, if we were to switch the 10 and the 6, with one being the width and the other being the length, we actually would get a different number this time. It would not be the same number, but that's how we designated our length and width at the beginning. So that's the answer that we got. Number 3, a right circular cylinder whose dimensions are changing has a height of 9 feet and a radius of 4 feet. Write formulas for the volume and lateral surface area of the cylinder and the rate at which they are changing at. So, and this moment in time, so at that moment in time. So we need to know the volume of a right circular cylinder. So the volume of a right circular cylinder is pi r squared times h. We're going to take the derivative of that using implicit differentiation. So we get the derivative of v is just 1 dv dt. I'm going to factor the pi out, and we're going to have to use product rule on the r squared and the h piece. So the derivative of r squared is 2r times h. We took the derivative of r with respect to time, so dr dt, plus the derivative of h is just 1 times r squared. And since we took the derivative of h, that's going to be times dh dt. For the surface area of a right circular cylinder is equal to 2 pi r times h. And we're going to have to use product rule again on the R and the H. So we get the derivative of S is just 1 ds dt. We can factor the 2 pi out. And the derivative of R is 1 times H times dr dt, plus the derivative of H is 1 times R dh dt, since we took the derivative of H that time. Alrighty, so now we're going to use those formulas to figure out what's happening as the radius and the height are shrinking and growing. So part A says the radius is growing at 2 feet per minute. So dr dt is equal to 2 feet per minute. And it says the height is shrinking. So dh dt is shrinking at a rate of -3 feet per minute. We're going to plug all of this stuff into the formula. Remember, it told us at the beginning of the problem that it had a height of 9 feet and a radius of 4 feet. So we also know that R is equal to 4 feet and H is equal to 9 feet. So now we can plug all these numbers into the formula. I'm not going to write the formula over again. We're looking for change of volume. So we are looking for dv dt in this case. And we are using this equation. So dv dt is equal to pi times 2 times the radius is 4 times h is 9 times how is the radius changing? The radius is changing at a rate of 2 feet per minute. So times 2, and all that information was given to me. Plus, how is the radius is 4. 4 squared is 16. 4 squared is 16 times dh dt, and the height is changing at a rate of -3. Typically, they're going to let you use a calculator on this. Could you do this by hand? You could. 16 times -3 is -48. 2 times 4 is 8. 8 times 9 is 72. 72 times 2 is 144. 144 minus 48 is 96. So we get 96 pi. And since we're talking about volume, volume is units cubed. So my units are going to be 96 pi feet cubed per, and our time unit was minutes. Change the surface area, we're going to do the same thing. We get ds dt. I'm not going to write the formula over again. We're just using the same formula as before. This one over here, so we get 2 pi times the height is equal to 9 feet times dr dt. How is the radius changing? The radius is changing at a rate of 2 feet per minute, plus the radius is 4 feet times how is the height changing? The height's changing at a rate of -3 feet per minute. So we get 2 pi times 18 minus 12. 18 minus 12 is 6. 6 times 2 pi is 12. So we get 12 pi. We're talking about area now, and area is units squared. So we got feet squared per minute. And that's how the surface area would be changing. We would do part B very similar. I'm going to skip it for the sake of time, but you should be able to look at that and figure out the radius is decreasing. So we know dr dt is equal to -2 feet per minute. And it says the height is increasing. So dh dt would be equal to 3 feet per minute. So the only thing that would really change in our formulas would be the numbers where dr dt here and here, dh dt, and in this other formula, dr dt and dh dt. That would be the only thing that changes in part B. Part C. Part C is a little bit different. If the radius is growing at 3 feet per minute, and the volume is not changing. So what do we know? They've given me a good bit of information here. What they've given me that dv dt, the volume is not growing, so that's equal to 0. They've also told me that the radius, dr dt, is growing at 3 feet per minute. And what are they actually asking for? How fast is the height changing? So we're actually finding dH dt. So what does dH dt equal? It says volume, so we're going to use the volume formula. So I'm going to write the entire volume formula over again that we came up with earlier. dV dt is equal to pi times r squared. Actually, I think we said 2RH dr dt plus r squared dH dt. So now they've given me enough information. We know everything that we can plug into this formula. The one thing we don't know is dH dt, and that's actually the what we have to solve for in this problem. We know dV dt is equal to 0, pi, 2. We know the radius is the same as before. The radius before was equal to 4 feet, so 2 times 4. The height was equal to 9. We know the radius in this problem is changing at 3 feet per minute, plus the radius is 4 squared. 4 squared is 16 dH dt. And that's all equal to 0. We can divide both sides by pi. And by dividing both sides by pi, the pi is going to go away. So we get 0 is equal to, we can multiply 2 times 4 times 9 times 3. And 2 times 4 times 9 times 3 is equal to 8 times 9, which is 72. And 72 times 3 is equal to 216. So we get 216 plus 16 dH dt. And now we're treating dH dt like a variable, and we're going to solve for dH dt. We're going to subtract 216 from both sides. So we get negative 216 is equal to 16 dH dt. And we can divide both sides by 16 to get dH dt by itself. So dH dt is equal to 216 or negative 216 divided by 16. So since it's negative, we know the height is actually decreasing in this case. And that simplifies to negative 27 over 2, or negative 13.5 feet per minute. Because the height, the units for height, is just feet. Part D, very similar problem. If the height grows at 3 feet per minute and the surface area is not changing. So what do we know in this problem? We know ds dt is not changing. That's equal to 0. We also know that dH dt is equal to 3 feet per minute. They're asking how fast does the radius change? So we're actually solving for dr dt, and we're going to use the surface area formula. The surface area formula from before was ds dt is equal to 2 pi times h dr dt plus r dH dt. That's the formula from before. So now notice how I wrote all this stuff out that we knew. We knew the surface area was not changing, so that's ds dt. And now that we know all of this, we can just plug it into the equation. The height was 9 feet, dr dt. That's what we don't know. That's what we're trying to solve for. The radius was 4 feet, and the height changing at a rate of 3 feet per minute. We can divide both sides by 2 pi, and the 2 pi is going to cancel out. That's really nice. And 0 divided by 2 pi is still 0. So we get 0 is equal to 9 dr dt, and 4 times 3 is 12. We subtract 12 from both sides. We get negative 12 is equal to 9 dr dt. And we can divide both sides by 9. Negative 12 divided by 9 simplifies to negative 4 over 3, or negative 1 1/3 feet per minute. How do I know the units are feet and not feet squared? Because we're talking about the radius. And if you talk about a radius, the units are a length and not something different.